Everybody. Welcome to a new video lecture from the series of TRACE project, tracing climate change by different geomorphological approaches. Today we have a lecture dedicated to coastal areas. My name is Florin Tătui. I'm coming from University of Bucharest. I'm associated professor there. And today we will speak about different methods of assessing coastline dynamics using remote sensing methods. And the first thing that we have to discuss is related to um, how to define the shoreline and why the shoreline is important. And here we have an idealized cross section of a wave dominated beach system, and you can see that on all the worldwide coast we have a subaerial part of the coast, which can have a beach, dunes, cliffs, and other landforms, and submerged part of the profile. Sometimes it's sandbars of other landforms. In between these two parts, the subaerial and submerged part, we have the shoreline, and the shoreline is very dynamic because it registers all the changes that happen both under the subaerial part and of the submerged part of the coast. And it is important to realize that this part, the shoreline or the waterline or the coastline, how it's sometimes called, is very dynamic. So it changes every time because here we have the wave action, we have currents, we have sediments coming from the beach. So we have a permanent movement of sediments back and forth. That's why this area is very dynamic. Here we have another diagram showing the components of a sandy beach, and you can see the subaerial beach with some berms and also the submerged part of the beach with the longshore bar. And here is the shoreline. So basically, let's have some examples. If we have movement of sand during summer from this longshore bar to the beach, we will have a movement of the shoreline offshore. So we have what we called progradation. So the shoreline is moving to the sea. During winter, when we have high waves, the sediments is eroded from the beach and it moves offshore. So the shoreline is moving onshore, is moving inland. That's why I said that this area is basically the interface between water and land, and it is very dynamic. So this is the main reason why it is very important to know the position of the shoreline, because it registers all these dynamic movements of the entire beach of the coastal system. And for instance, if something is happening like an erosion in the underwater part of the profile, it will definitely be registered by the shoreline. So the erosion will also come here, and we will have a movement of the shoreline to the beach. So it's very important to know all these processes and to be able to account the position of the shoreline, as you can see here in this more complex diagram. Yeah, and here we have the shoreline dynamics controlled by the sediment transfer from the submerged part of the profile to subaerial part of the profile and vice versa. Of course, there are many methods that we can employ in order to um, analyze the shoreline dynamics. And in the past, the most important tool that we used is related to maps. Here we have some examples of maps from the Danube Delta in the Black Sea in Romania. And the first map you see was made by the European Commission of the Danube in 1856. So it has more than 170 years. And of course, if we georeference it very well, we can track the shoreline. So basically we can have an information about the position of the shoreline 170 years ago. And you see different maps that were done afterwards at the beginning of the 20th century and at the end of the 20th century. What we have done here at University of Bucharest with this map, so we georeferenced them, we digitized we extracted the shoreline, and here you can see two different products with shoreline dynamics in between two sets of maps. And for instance, in this area you can see a continuous erosion from 1856 to 2003. You can see accumulation in this northern part of Kilia, and the dynamics of this spit, which is called Sakhalin spit, is detailed here. And you can see its evolution from 1898 to 2013 through continuous elongation and also rollover. So transverse movement to the mainland. Um, when we have, let's say, different generations of shorelines extracted either from maps or from other sources, it is very important to track these differences and to track their dynamics, which is not always easy. But the most used tool in order to do this, it is this shoreline digital shoreline analysis system, this SAS, which works in ArcGIS. And you can see here an example with 365 transects spaced at half a kilometer for the whole Danube Delta coast. And basically on each of these transects intersecting different shorelines, you can obtain the dynamics, and I will show you immediately some results. You need to have a baseline. For you have an example here, a baseline with black, and afterwards you see we have three different shorelines from 1855, 1925, 1980, and another one from 1997. And we have these perpendicular transects, and we measure the distance in between two consecutive shorelines on each transect, and we can obtain different metrics. For instance, one of them is the net shoreline movement, which is basically the distance between oldest and youngest shorelines, the endpoint rate, which is the ratio between this net shoreline movement and the time between oldest and most recent shoreline, or the shoreline change envelope, which is the greatest distance between all shorelines. And you can see here different examples about this. Here we have an example of the result of such an analysis made with this SAS on the Danube Delta coast. In this area we have many erosional sectors which are marked in this figure with red rectangles, and some accumulation areas marked with blue rectangles. And on the right hand side, we see the evolution of the shoreline between in different time periods with as you can see here erosion in this area. So this area is this one, and we can see continuous erosion between 1979 and 1997. And here are some metrics, some data. You can see that in the first part, 1961, 1979, we had up to 15 meters per a year. For instance, here 14 meters per year here on average, or 23 meters per year for the Sakhalin speed, with maximum values exceeding even 30 meters per year. And these values were so high because there was a very stormy period that time, and you can see that afterwards in the following decades these values decreased, but they still remain high for a sandy beach. And also the same situation for the accumulative accretional sectors. So basically, this is an example of how you can use digital shoreline analysis system in order to get some data related to the dynamics of the shorelines in an area. And here is, let's say, another result for the whole Danube Delta coast between 1856, 1979, and afterwards. And you can see different dynamics, and you can find more information about this and more details in the references that are attached to this video lecture. Also, another type of result, if you have many shorelines, you can track along shore. You can track the dynamics of the shoreline, and you can see, for instance, in this area, which is this area Kilia, you can see that after a long period, like 100 years of accumulation, the accumulation decreases, and instead we have erosion, because basically we do not have enough sediments from the Danube because of the construction of dams in the whole Danube basin. There are not enough sediments in order to sustain the development of this lobe of the Danube Delta in the future, and also different dynamics on other sectors. I will not go into details. If you are curious, you can find details about this in the references. Also, here is a visual representation for Kilia Lobe. You can see the shoreline estimated for 7050, and you can see this explosion of Kilia Lobe. But from the 70s, there is no expansion of this lobe, but we have like erosion, which you can also see here. So after this period of um, movement offshore, so accumulation, high rates of accumulation, we have a decrease in this accumulation, and also uh, uh, even erosion in the last decades. So we spoke about the methods that were used and are used for, let's say, the data that are um, quite old, because besides maps we cannot find many information. For instance, for 100 years ago, we can find some information from the, let's say, half of the 20th century, because there are some satellite images available, and you can search for corona images, which are some American images from the 50s and 60s. And afterwards, of course, we have maps, we have satellite images, we have aerial images in some countries, and also in situ measurements. And here uh, we have an overview of the modern methods for shoreline extraction. It's from an article by Vitusek and collaborators in 2022. You have it in the references, and you can see that there are many different methods for shoreline extractions, from aerial photos, also in situ surveys with GPS, RTK. Also, we can use fixed cameras in order to obtain remotely this information about the shorelines. In the last years, there are some crowdsourced tools like the Coast Snap. Basically, you take a photo of a beach, and you can obtain the shoreline there. You can Google it, and it's very, very nice. We can also use the extraction from motion from the drones, aerial photogrammetry, airborne lidar, Earth observation satellites, and we will speak about this today, basically, and also CubeSats, which are another type of satellites. Um, Here we can see each of these methods, what temporal and spatial scales are they covering, and I will focus only on the Earth observing satellites, and we can see here in this green square that the Earth observing satellites help us to cover the highest spatial scales and also the highest temporal scales. So basically, we can cover areas from meters to hundreds of kilometers, maybe more than 1000 kilometers, and spatial and temporal scales from hours and days to decades. So there is a large, let's say, palette of temporal and spatial scales, and that's why the Earth observing data are very important nowadays. And on the left hand side, you can see different coastal processes that are happening at these temporal and spatial scales, and of course many of these can be analyzed based on satellite images. Related to the automated methods for shoreline identification from optical satellite images, we can go at pixel resolution. So, for instance, if we have a pixel of 30 meters, we can track it with the shoreline with this pixel resolution, or we can employ some um, machine learning and other tools in order to improve the quality of that image. And you can see the difference in between these two images. On the left right hand side, sorry, we have an image at sub-pixel resolution, and you can see that the shoreline is more smooth. It's smoother than on the left hand side image, because we are going at a sub-pixel resolution, but we have to work more on the image. We have to employ some machine learning methods in order to improve the quality of this image. And of course, in the end, after obtaining all these shorelines, we can introduce them in some kind of operational tools that can predict the shoreline dynamics for the future. And from the same paper of Vitusek and collaborators, we have this example uh, of an workflow from an image, obtaining based on the segmentation of that image, obtaining the shoreline, and also combined the shorelines combined with the wave hindcast and wave forecast. We can predict, you can see here, we can predict the position of the shoreline. So we have the position of the shoreline, you see, from 2014, 2015, 16, and then for this area we can forecast it based on what happened before and on the combination between the shoreline dynamics and the forcing, which is given by the waves. Just some short notice about the spectral bands, because these satellite images have different spectral bands, and in order to get the shorelines, you'll see in a couple of minutes, we have to combine these spectral bands in order to obtain the best combination to extract the shoreline. And basically what we want to obtain is a difference between water and land. So a clear difference between water and land, which is the position of the shoreline. And we have here two examples. Sentinel-2A, a satellite. It has 11 spectral bands from blue, green, red, near infrared, and shortwave infrared, and the Landsat 8 satellite with 7 spectral bands. And you can see that, of course, each spectral band has a wavelength range and also a special resolution. And Sentinel-2 has a better special resolution, 10 meters, compared with Landsat, which is very, very good. So the optimal situation is to have a good special resolution. So if it's going to 1 meter, it's better, and also a very good radiometric, what we call it, resolution. So many spectral bands in order to be able to combine them and to obtain that difference between water and land. And now I will show you a study case on estimating shoreline position on the Danube Delta coast. It is an unpublished work done by my colleague Sorin Constantin, myself, and other colleagues, and we employed this method on the Danube Delta coast between 1990 and 2022, and we used both Landsat satellites from 5 to 8 at 30 meters spatial resolution, and also Sentinel-2 satellites at 10 meters spatial resolution. And when we started a couple of years ago this study, there were 2 phases employed. So first phase, we tested different methods with some indices, supervised and unsupervised classification, image segmentation, and then in the second phase we chose the best method, which was this automatic water extraction index, based on the work done by FEISA collaborators in 2014. And we extracted the water length threshold for each image, and also we estimated shoreline position at sub-pixel resolution. So we obtained some data at less than 10 meter spatial resolution. What were the approaches tested during phase 1? So we derived both optical and radar, synthetic aperture radar images, using 3 different algorithms. First one, waterline detection using 2 spectral indices, normalized difference water index and modify normalized difference water index. The second algorithm, waterline detection using a supervised classification, and the third one, waterline detection using binary products from radar images. And in total, we derived 22 waterlines using these three algorithms. And uh, you can also see what were the satellite images used, type of satellite image, optical and radar, what were the algorithms used for each satellite image, and the indicator date. First algorithm was the waterline detection based on optical data, and here we have an example using the normalized difference water index. And I told you basically we want to track this difference between water and land using these two NDWI and MNDWI indices. You can see that there is not a very clear a difference, so sometimes we can have some errors. um, the second approach that we tried to employ was the waterline detection using a supervised classification products. So basically, you train a model and you say to it that this is land, this is land, this is water, this is water, this is water, and afterwards it classifies the whole image into these two categories, land and water. And we use this classifier, maximum likelihood classifier algorithm, on the different spectral bands, and we extracted the interface between the two typologies, land and water. And the third one was the results were not very good here, because yeah, the algorithm didn't work very well. And the waterline detection using binary products from synthetic aperture radar amplitude data. You can see here the workflow that we employed with some minimum values between vertical and vertical horizontal polarization computed. And then you see here some examples, and as you can observe, yeah, it doesn't work so well. Afterwards, we did some validation activities. Of course, we have to compare the results obtained using our algorithms with the result with some measured data, and we saw that the supervised classification method performed better than the index-based approach. Um, However, the index-based approach can be improved due to errors being determined by constant shifts. And one important conclusion was that the radar-based results were not satisfactory, so we didn't took them into consideration for the next for the second phase. The second phase was focused on index-based approaches, and we use that modify normalized difference water index and another index, automated water extraction index, from this paper of ESA and collaborators, which combines the green, sorry, short wave infrared and near infrared spectral bands according to this formula. And we worked at both pixel and sub-pixel resolution on level 1 and level 2 satellite images. And in the end, we applied the an automated thresholding technique, which is the Otsu method. And you can see here three different examples of water lines derived from Sentinel-2 data using this automatic water extraction index over different moments in 2016. And you can see that it performed very, very well. Either for an image like here where we have wave breaking, or for images where we do not have wave breaking. It tracks pretty well the shoreline. And for validating this, we used 5 Sentinel-2 and 5 Landsat-based results compared with in situ measurements and also with data extracted from very high resolution images like Pleiades at 0.5 meter spatial resolution and Spot 7 at 1.5 meter spatial resolution. Both Pleiades and Spot 7 are not free satellite images like Sentinel-2 and Landsat. Pleiades and Spot 7 are some commercial satellites. And you can see here different metrics for this combination, an image from 18 February 2016, I think is this one, and in situ data from 27 February, so at 9 days difference, and we can see this mean absolute error at subpixel resolution 4 meters here, and for automatic water extraction header index even less than 3 meters, let's say, difference, which is very, very good. So the main conclusion was that this automatic water extraction needles using level 2 data, so processed data, was the best approach with mean absolute errors lower than 7 8 meters, both from Landsat and Sentinel-2 images. And you can see here other validation examples with extracted data and in situ data for Landsat 8, Pleiades, in two different areas. And here are the histograms, and here you can see that the errors are for Aave are very, very low. Uh, Also, other validation examples: Sentinel-2 against in situ collected data. Again, root mean square errors of around 3.5 meters for automatic water extraction index. And here other examples for for Landsat 8 against very high resolution imagery Pleiades, and still we have very small errors. And here are all data for all the validation examples, and as you can see, for all this data we have a average root mean square error of 6.42 meters and a mean absolute error of less than 5 meters. So basically in all these pairs of automatically extracted shorelines versus the measured shorelines, we have an average difference of less than 5 meters for both Sentinel-2 and Landsat, which is very, very, very good. And now we will see some examples. In the end, we extracted more than 220 Landsat and Sentinel-2 images for the entire Danube Delta coast between 1990 and 2022, so 32 years. And you can see here two examples of the shoreline. So each yellow line represents an automatically extracted shoreline. So afterwards, my colleague, here is another example, and other examples have differences between 1990 and 2020 for different areas of the Danube Delta. And in the end, what we can do is tracking on the transects that I showed you in at the beginning of this lecture. We can track the dynamics. So basically in each of these graphs each blue point is the position, actually the intersection of each shoreline with that transect. And for instance, here we can see that we have a retreat, a general retreat, erosion of the coast. So retreat of the shoreline with an annual rate of 3.28 meters. Here also this retreat. In other parts we have an accretional trend, so a movement of the shoreline to the sea with rates reaching, in this case for instance, 3.62 meters per year. What we can also see, for instance, here is that we had some storms. So this very rapid decrease means that here in 1997, 1998, we had a big storm which created erosion also here. So another information that we can obtain is related to individual events, to individual storms. And overall, if we put together all this data, we can obtain an average change rate in meters per year, as you can see here. So basically, we can see that most of the Danube Delta coast is retreating in these areas up to 10-11 meters per year. In this area 5 to 10 meters, 5 meters in this area, and we have accumulation on certain areas. And here, using a Hofmöller diagram, we can track this. With red we have erosion, and with gray we have accumulation. And what we can see is the dominance of erosion on all these sectors. And also, coming from 1990 to 2020, we can see a spreading of the erosion. So the erosion becomes dominant on more sectors along the Danube Delta coast. And this is a result of basically the automatic extracted shorelines. And this is a synthetic image of what is happening in this area north of Sfântu Gheorghe arm of the Danube, and this was published on the European Space Agency website. And we can see how the dynamics affects the coast along shore. We can see here a slightly accumulative sector in the immediate vicinity of the mouth, and to the north we can see strong erosion with average annual rates exceeding 1 meter per 10-11 meters per year. So if we conclude what we have seen before, the main advantages of automatically extracting shorelines from satellite images are related to the fact that we can process a large quantity of satellite data. So hundreds and hundreds of satellite data, and we can cover long periods of time. Basically, we can go back to the 80s. So the Lancet mission started at the beginning of the 1980s, so 1983, 1984. So we have today like very good data that we can use for the last 40 years, for the last 4 decades. Also, we have errors, but while they are present, they are systematic due to low human intervention, because all you have seen is basically an automatic process. And the analysis of large areas, like hundreds of kilometers, is possible using this algorithm, and also using other algorithms. Like resources, you have here a list of resources that you can follow, there is a very well known tool that can be used in order to extract shorelines, which is called CoastSat. You have here the most important links related to this CoastSat. You have some papers in the references list, and also related to this video lecture, you have an exercise. There is a tutorial and also a database that you can use, and you can see there how to use this COSAT tool in order to extract shorelines. You'll see it's very easy to follow. Also, there is a worldwide database of shorelines which is called Shoreline Monitor. You can find it at this link. Also, there is a shoreline analysis and extraction tool, SAET. You can find it here. A coastal analysis system from Space Imagery Engine, CASI. It has many different things, not only related to shorelines, and you have the link here, and also the high tide satellite derived shorelines at this link. Thank you very much for your attention. If you have questions, you can always contact me at this email address, and please follow the reference list that is related to this video lecture, and also I advise you to follow that COSAT exercise, which is very nice, and I think you'll like it. So thank you very much. All the best.